Hello friends, I welcome you on my lecture series for the subject probability and statistics. Today we are going to discuss about expected value or mean of a discrete random variables. So in previous lectures we have discussed about discrete random variables, its probability mass function and its distribution function. So today we are going to discuss what is meaning of mean of a discrete random variable, and we will do some examples based on this definition. So first we see the definition of expected value of a discrete random variable. So suppose x is a discrete random variable with probability mass function small p of x. Then the expected value or mean of capital X is denoted by expected value of x, that is E of capital X, or another notation is mu suffix capital X, or simply we can denote it by small mu also, and is defined as mu equal to sigma x into value of PMF at point x. So it is nothing but summation of this type of terms. Each value of random variable x is multiplied with corresponding probabilities. So it is a mean, but here p of x is serving as a weight. So we are taking sum of all the possible values of random variable x which are multiplied with their corresponding probabilities. So this is one kind of weighted average where these probabilities are working as weights. So you can easily find out mean of any discrete random variable if you know its probability mass function. So as I said, the expected value of x is a weighted average of the possible values that capital X can take on, each value being weighted by the probability that capital X assumes it. That means this p of x is nothing but probability that capital X equal to small x. So these probabilities are working as a weight for this definition. We consider one example. Find the expected value of the random variable capital X if x is the number on a fair die when thrown. So here the experiment is we are throwing a fair die. So random variable is defined as the number on a fair dice. So when we are throwing a dice, there are 6 possibilities. Either 1 occurs, 2 occurs, 3 occurs, 4 occurs, 5 occurs, or 6 occurs. So the number on the upward face of a dice can be any number from 1 to 6. So the possible values of this random variable are small x equal to 1 to 6. Now probability of each outcome, suppose 1 occurs, then the probability that x equal to 1 occurs is 1 divided by 6. Okay, that we have already discussed. Suppose I want to find out value of probability mass function at x equal to 1, then by definition it is probability of this event, capital X equal to 1. That means 1 occurs when a dice is thrown. So total number of possibilities are 6 and the outcome in favor of 1 occurs is only 1. So probability corresponding to small x equal to 1 is 1 by 6. Similarly, if we consider capital X equal to 2 here, then also there is only one possibility that 2 will occur and total number of possibilities are 6. So value of p of 2 is also 1 by 6. Similarly, value of probability mass function is 1 by 6 at each possible value of this random variable. So we can generally write probability mass function as p of x equal to 1 by 6, where x is any value from 1 to 6. Now if I want to find out expected value or mean of this random variable, then I will use the definition. By definition, expected value of x equal to sigma x into p of x. Now here p of x is 1 by 6 for each value of x. So we put 1 by 6 here. It is same for each possible values. Now this summation depends on variable x. So we can take 1 by 6 outside. So we have to sum up to 6. This is sigma x. X is running from 1 to 6. So 1 plus 2 plus 3 plus 4 plus 5 plus 6. So either you can sum all this or you can use this formula. Summation of first n positive integers is given by, this is nothing but summation of first natural numbers 1 plus 2 plus 3 and so on up to n. So sum of first positive integers is given by n into n plus 1 by 2. Here we have sum of first 6 positive integers. So in this formula we have to take n equal to 6. So if we take n equal to 6, we will have 6 into 7 divided by 2. And this 6 will cancel out, and 7 by 2 is nothing but expected value or mean of this random variable. So it is easy to find out expected value or mean of a random variable. You just have to remember this definition. And if probability mass function is not given, then also you can decide it using the definition of probability mass function. We consider one more example. Suppose the probability mass function of a random variable x is given by p of x equal to small p into 1 minus p raised to x minus 1, where x is any natural number. And if x is different from these natural numbers, then value is 0. That means possible values of random variable x are small x equal to 1, 2, 3. Here I have denoted this probability mass function by this suffix x because p is used here. So to distinguish these two, we are using this notation for probability mass function. This capital X corresponds to the variable x, discrete random variable capital X, and this p is nothing but real number between 0 and 1. It is the probability. And using this PMF, we have to find out mean of random variable capital X. Okay, so again we go by definition. Mean is nothing but summation of x into px, where here range of x is 1 to up to infinity. For other values, probability mass function is 0. And p of x is p into 1 minus p raised to x minus 1 if x is natural number. So we substitute that value here. Now in this xp into 1 minus p raised to x minus 1, this p is independent of x. So we can take p outside summation. Now to find out this infinite sum, we rewrite this 1 minus p raised to x minus 1 in this form. Okay, I am rewriting this whole term by this. Okay, you can see derivative of, okay, if I take negative sign, and derivative of 1 minus p raised to x. So derivative of 1 minus p raised to x is, derivative is with respect to p. So minus x 1 minus p raised to x minus 1 into derivative of 1 minus p, that is minus 1. So minus minus will be positive and we will obtain this. So derivative of this term 1 minus p raised to x is nothing but x into 1 minus p raised to x minus 1. and we have to take negative sign. So using this, now in the next step we interchange this summation and derivative. So summation of derivative equal to derivative of summation. Now we expand this series. X is running from 1 to infinity, so it is minus p derivative with respect to p of this bracket. This bracket is nothing but this infinite series. So for x equal to 1 it is 1 minus p, for x equal to 2 it is 1 minus p square, and so on. So you can see this is nothing but geometric series. And if you recall, if we have geometric series a plus ar square and so on, then if modulus of r is less than 1, then sum of this infinite series is given by first term, that is a divided by 1 minus r, where r is the common ratio. So if we compare this series with this geometric series, then we can see a is 1 minus p and the common ratio is also 1 minus p. If you take ratio of any two successive terms, then it is going to be 1 minus p. Now it is given that p is in between 0 and 1. That means 1 minus p is also number between 0 and 1. So this implies modulus of 1 minus p is less than or equal to 1. So therefore we can apply this formula here. 1 minus p is in between 0 and 1. So this is nothing but a divided by 1 minus r. A is 1 minus p divided by 1 minus r, that is 1 minus p. Okay, so using this geometric series with a equal to 1 minus p and r equal to 1 minus p, and if you simplify this, 1 will cancel out and we will have small p in the denominator. So this is minus p d by dp of 1 minus p divided by p, and this I can rewrite as 1 divided by p minus 1, and if we differentiate, derivative of 1 by p is minus 1 by p square and derivative of 1 is 0. So we obtain 1 upon p. So expected value of capital X is 1 by p. Okay, we can make some remarks here. Expected value of random variable x is also known as expectation of capital X. In some books, authors are using mathematical expectation also. So all are synonyms: expectation of x or expected value of x or mean of x, average of x. Now suppose x is a discrete random variable with probability mass function p of x. Then for any real valued function hx, if we want to find out expected value of h of capital X, then it is given by summation hx into px. So here we are using the fact that if capital X is a random variable, then if h is any real valued function, then h of capital X is also a random variable. Okay, I repeat again, if x is a random variable, then for any real valued function hx, h of capital X is also a random variable. Now how to find out expected value of this new random variable? So you can remember this. We can prove this also by the definition, but we are not going into the details of proof. We just remember that expected value of function of a random variable equal to sigma h of x, means this small x is the value of this random variable. So we are taking value of function h at point x. So h of x into p of x. And if if our this function h of x is a linear function, then expected value of ax plus b is nothing but a into expected value of x plus b. That means expected value of x is a linear function. We can take this a outside, so a into expected value of x plus b. This we can rewrite in another notation as mean of random variable ax plus b equal to a into mean of random variable x plus b. So we take this example. Suppose the random variable capital X has the following probability distribution. So x is given and corresponding values of probability mass functions are given. So we have to find out expected value of x square. Okay, so if you recall this expected value of function of x equal to, okay, so here function of x is x square. So h of x is x square. So this is going to be sigma hx is x square into p of x. Okay, so using this remark, we can write expected value of capital X square is nothing but sigma x square into p of x. So we use that fact here, sigma x square into p of x. So we have to multiply square of minus 1 with 0.2, square of 0 with 0.5 and square of 1 with 0.3. Okay, so that we have written here minus 1 square into probability at point minus 1 plus 0 square into p of 0 and 1 square into p of 1. Then we have put values of p of minus 1, p of 0 and p of 1, that is 0.2, 0.5 and 0.3, and we obtain 0.5 as expected value of square of random variable. Okay, so here we are using that note hx is any, here the function is x square. So h of capital X is going to be capital X square, and we are using this remark. So h of x is x square. Okay, so instead of x square you may have any real valued function. You can use this formula to calculate expected value of function of a random variable. This is another remark. Expected value of a random variable x is also known as the first moment of x. This is another name for mean or expected value of a random variable. It is also known as first moment of a random variable x. In general, if we take nth power of random variable x and then we find out expected value of x raised to n, then it is known as nth moment of random variable x, and it is using that remark. Instead of h of x, your function is h of x equal to capital X raised to n. Okay, so using that remark, this is nothing but sigma small x raised to n into corresponding values of probability mass function. So this is nothing but nth moment of random variable capital X. So in this example, this is nothing but second moment of random variable x. Okay, we have calculated second moment of random variable capital X. Okay, so in this way you can calculate nth moment of a random variable x, where n is any natural number. Next example, let capital X be a random variable with the given probability distribution. So values of random variable and its corresponding probabilities are given, and we have to calculate this expected value of x, expected value of x square, and expected value of 2x plus 1 square. So by definition, expected value of x is summation x into p of x. So we have to take minus 3 into 1 by 6, 6 into 1 by 2, 9 into 1 by 3, and after simplifying we obtain 11 by 2. Similarly, expected value of x square is summation x square into px. So here I have to take square. Okay, these are the values of x, minus 369. So instead of minus 369, I will write minus 3 square, 6 square, 9 square, and corresponding probabilities are as it is. So if I simplify, I will obtain 93 by 2. So I am not going for the calculation part. Next one is expected value of 2x plus 1 square. So here function hx is two into x plus 1 square. Okay, so if we replace capital X by small x, we will have 2x plus 1 square, and this is going to be sigma hx into px, and hx is 2x plus 1 square. This is hx, and into we have to multiply p of x, that is probability mass function of x. So again we are using that remark here, this remark, expected value of a function of x is nothing but sigma h of x into p of x for any real value function hx. So here hx is nothing but 2x plus 1 square, 2x plus 1 whole square. So using that remark we are able to find out this also, 2x plus 1 square into px. Now values of x are minus 3, 6 and 9. So first we put x equal to minus 3. So 2 into minus 3 plus 1 square into p of minus 3. Second value of x is 6. So 2 into 6 plus 1 square into p of 6. Third value of x is 9. So 2 into 9 plus 1 square into p of 9. And then after simplifying all this and putting values of p of minus 3, p of 6 and p of 9, we will obtain that expected value of 2x plus 1 square is 209. So in this way you can find out expected value of a given random variable x as well as expected value of a function of random variable capital X. So I hope you understand this lecture. If you have any doubt, you can write in the comment section. In the next session we are going to discuss about variance of a discrete random variable. Thank you very much.